Hey, so I'm Matt Onelaw, and I'm going to be talking about incremental view maintenance. What incremental view maintenance is, it's the ability to query your database, and then anytime your database changes, rather than having to rerun the query gets automatically updated as write events are processed. So it makes it very efficient to do subscriptions because you're no longer having to rerun queries from scratch anytime some state changes. So why am I talking about incremental view maintenance at a local first conference? The main reason is all apps are really just views over data. So you can look at some examples, right? Like WhatsApp. You have a thread list, and that thread list shows the name of the person on it and maybe the last message they sent. Well, really that's just a query over the WhatsApp data, where to compose this view, we're selecting the thread name, we're selecting the participants, and maybe we're selecting the last message in the thread and using that to then compose the UI. And same thing for Spotify, right? We're selecting to display our track UI, we're selecting all the tracks, maybe we're joining in or sub-selecting the artist to get all the artist names. Yeah. And back in the old days, right, in the LAMP stack or Rails, every time you visit a page, it'd be a full page refresh, and you'd run these queries from scratch. Today, people have very rich, long-lived sessions where every time you're interacting in one of these sorts of apps, there's no refresh going on. The view is updated in place. So ideally, our UIs could subscribe to these queries, and whenever we do a write to our database, these queries would tell the UI, hey, here's the new result of the query. Go ahead and update yourself or re-render yourself. So yeah, as state in the database changes, views should automatically update. And this should also be efficient, right? We shouldn't have to rerun. If the database changes, we shouldn't have to rerun every single query in the app. The queries that are impacted by a given write should be updated, should be patched in place without any rerunning. So IVM is the process by which we can do this. And you can think of it as a dependency graph, like signals. So if you're familiar with Solid, right, they use signals. Signals creates this graph of computation. So if one atom changes, it only runs a subgraph that depends on that atom and not the entire subgraph. The big difference with IVM is it knows how to do incremental computation over collections. So if one of your atoms is a list of 1 million items and you modify one item in that list, well, IVM won't reprocess the full list, it'll just process the one item that changed. So kind of to drive that home, give you an intuition, we can think about these operations and how we do them without IVM. So if you had the set X and you map it and you filter and reduce it, well, each one of these steps is creating a copy of the array. We're copying the array to map it, we're copying the array to filter it, and yeah, I guess we're not copying it to reduce it. But as this pipeline gets bigger with more maps and filters, any modification to X results in N array copies, where N is kind of the depth of map and filter operations. And without IVM, another example is more closely related to querying. Say you have a issue set and it has 100,000 issues in it, and you want to find all issues with the foo title. So maybe you have an issue UI and the user has typed in to filter it down to just issues with foo. And while that's happening, maybe you're collaborating, right? Local first is all about collaboration. And your collaborators are modifying issues, creating new issues, deleting issues, and you want your UI to respond to that. Well, it'd be unfortunate if every time a new event came in from a collaborator, you had to rescan your full 100,000 items. It would be ideal if only that single modification was processed and not the whole array of 100,000 things. Yeah, so I'm going to go over a very basic way of implementing an IVM system, just to kind of give you an understanding and intuition for how these sort of things work, and if you need to adopt some of the techniques in your own software, you want to go learn more. So some of the terminology, we have pipelines. So a pipeline is a chain of computations. Map, filter, reduce. x.map.filter.reduce would be a pipeline. A source is the thing that provides data to the pipeline, so the collection at the beginning. An operator is just a node in the pipeline, so any of these are operators that are in the pipeline. A view is the final result of the pipeline. So once the pipeline's done, you have kind of your view of the new data. And a difference is a change that's sent through the pipeline. So in like normal JavaScript, right, you call map, it creates a copy of the array, it sends it to the filter step, creates a copy of the array, it sends it to the reduce step. In IVM, rather than sending copies of the array, X is sending difference events to map, map is sending difference events to filter, filter is sending difference events to reduce. So as something is added to your source, a new difference event representing that add is sent, and everybody just operates on the single difference event that represents the modification. So here's a simple pipeline as an example. We have numbers, we're mapping it to double all the numbers. So our source is the numbers array. Our operator is the map operator, and our view is the set of doubled numbers. So yeah, how can we make map incremental? Well, a nice thing is map is actually already incremental because map only has to consider the single value it's operating on. It doesn't have to consider the entire collection. But the big problem is, how do we preserve a relationship between the source and the view? If you modify array index 10 in the numbers source, how do we understand that we should also modify the corresponding array index 10 in the view and pass that information down? And yeah, that's pretty trivial with map, but what if there's filters in place that remove items? So array index 10 in the source is not array index 10 in the view. It might be 5 or something. Yeah, so this is kind of a visual thing of what I just talked about. We have this array on the left. We want to change 30 to 25, and then we want to understand that that should update the corresponding 60 and replace it with 50 on the right-hand side. So to preserve that view and source relationship, so you understand what change in the source should correspond to what change in the view, you have two options. You could make sources and views maps of keys and values. So the most trivial way is like the key is a UUID and the value is the value. So that way, you know, oh, I changed this thing. Well, it's keyed with this ID. So once I get to the view, I know I need to update the thing that has the same ID. And yeah, so that way, even if this was filtering, say this was, I don't know, filtering every other number or something, and the view is a different length, well, we could use the IDs to understand, okay, well, which item to remove. The second option is to use a comparator on the source and view to just keep them in sorted order. So it knows when receiving an event in the view, based on its value, if there's a value in the view that's already equal to it, that should be, you know, replaced or updated or removed. Yeah, so modeling deletes, updates, and adds. It's a difference event. The difference event has a type, add or remove, has its value. If you use the map approach, it would also have a key. If you're using the comparator approach, this is all you have for your difference event. But if you do use the comparator approach, then update must be modeled as a remove followed by an add. And I'll discuss that more. So if we put it all together in an example, we want to replace 30 with 25. So we're going to model this as a remove. We want to remove 30. We remove it from the source. We pass it through the pipeline. The pipeline would have to be deterministic in the comparator case, so it gets the same value that it had last time. But this time, instead of that same value is coming with a remove event. So we say, oh, the view sees there's 60. I have 60. I need to remove it. And then the second event comes in. We add 25. It goes through the pipeline. It goes to the view. With the new value 50, the view has a comparator. It knows where to put it in the array in sorted order. Yeah, so filter can be implemented the same way as map. Join and reduce are the interesting and complicated operators because they require some form of memory. They don't operate just on a single row. Yeah, and what if you want to handle duplicate entries? So we have these collections. They're ordered by comparator. Somebody passes you remove 60. Well, what if you have 5 60s, not just 1 60? How do you know which 60 to remove? Well, you can change your difference event. Rather than having a type of add remove, you have a multiplicity, and that's just a number where the negative version of the number is remove the thing, that many times, the positive number is add it that many times, and a 0 is a no op. So, right, and I guess last thing is like, you have some basic intuition on like how you can do incremental map, filter, reduce, and, well, at least map and filter. We don't have time to get into reduce and join. But how would you model a query language just with these primitives? Well, these primitives are capable of arbitrary computation, so you can really map any query language you have to these sets of primitives. So as an example, we'll go through SQL. A select is really a map function where you're taking the input row and you're constraining what you're pulling off of it to a subset. Where is the same thing as filter. And is just filters chained together. So we want to select from issue where priority is 1 and status is 1. Well, that's filter priority 1 dot filter status equals 1. Or is a little more complicated than and. You can think of or as a union of two computations or a union of queries. So select all from issue where priority is 1 or status is 1 is the same thing as select all from issue where priority is 1, union select all from issue where status is 1. So you can kind of see where I'm going with this. You do issues filter by priority dot concat or union with issues filtered by status. Now you have two sets of issue lists, one by priority and one by status, all combined into the same list. And the final thing you'd have to do is distinct it, because maybe there's an issue with priority 1 and status 1, like it has both these set to 1. It would appear twice since you concatted both streams, so then you distinct them. Group by is just a reduce operation where any aggregation is reduce. And then join and reduce, right, we haven't really got into, but join is a custom operator that conceptually it's just combining two streams. So I don't know, you could just give you a kind of a vague idea of how it works. You could implement it with map, where for every row, you look at the other source and get a corresponding item of that source. So for every row in one source, you look at another source, get the corresponding item, and return the combination of the two. Of course, there could be multiple corresponding items, and you'd also want this to update if either issues or users changed. Yeah, so I guess the basic idea for modeling SQL, map each language construct, incremental filter, map, reduce, join, and then wire these things into a DAG. So you can then pass difference events between them. So a simple DAG for a select from issue, join issue labels, join label, where label's red, right? You've got your issues going to a join operator, the issue joining with the junction table, and then that result joining with the labels, and then that going to a filter, and then your final view. And as these sources change, they'd pass difference events along their edges, and those difference events would flow in and give you the new, and then patch up the view. Cool, so I'm going to give you a quick demo of a incremental query language that we've been working on called SQL. So what I have on the left is SQL, and the right is SQLite. They both have a table of 10,000 issues, and those issues have labels. And what we want to do is do a query for all the issues and their labels. So with limit 100, order by modified, limit 100. So I can show you on the left that with SQL we have our issues, we have our labels. This one has 2 labels. This is, yeah. And then we can do the same thing on the right with SQLite. And yeah, it returns as a flat array, but same thing. Issue 0 has label 0, issue 1 has label 0, 1. Kind of same as we saw over here. And there's 100 items. Cool. Yeah, so in an app, if say you have an issue list that's showing these issues in their labels, and as the data is changing, you want that issue list to update and reflect those changes. Well, in SQLite, you're going to have to rerun the query every time there's a change in your database. And whereas SQL, it'll incrementally keep things up to date. So let's show an example of the performance difference between that. So here we're going to measure SQLite. We're going to kind of mimic this case. We're going to do set an issue, and then we're going to rerun our statement for our issue table, and then we're going to benchmark that. And we're going to see how many times we can do this in 1 second. So wait for that to finish. All right, SQLite ran for 1,000 milliseconds, 1 second, did this 64 times. And then we'll do the same thing with SQL, where we're setting the issue, we're taking our statement again, we're re-executing it, and we're doing that for as many times as we can in 1 second. And let's see how fast we can do it with SQL. And yeah, so SQLite did it 64 times, SQL did it 64,237 times. Yeah, so essentially, rather than having to rerun the query, SQL is just taking the individual write and patching up your query results. It doesn't have to rerun the query every time. Yeah, so that was kind of a whirlwind talk. A lot of ground covered, but I guess the key takeaway should be you can make, map, filter, reduce, join, all these things incremental. You can preserve a relationship between your inputs and your outputs, so you can patch up your outputs. And since these operators are pretty generic computationally, you can model almost any computation you want with them. And if you're interested in further resources, VMware has a really good paper on kind of incremental view maintenance for arbitrary query languages. And then adapton.org has a lot on signals. And then our new product, which will eventually be coming out and open sourced, is called ZeroSync, and we'll have an implementation of Zero Query Language in it. So thanks for having me. I was glad I was able to give a talk, and hope you guys enjoy the rest of the meetup.